We'll go ahead and get started. Our first speaker is Erin Worth. She's with the USGS, based out of the University of Washington, the Department of Earth and Space Sciences. She's a geophysicist by training, and she works on strong ground motions. And she's going to be talking tonight about general earthquake science here in Western Washington, the Puget Lowland, and earthquake hazards in general. So, Erin, please come on up. You want this mic?
Can you hear me? Okay. Is this good volume? Great. Well, thank you very much for coming tonight. So as Brian said, I'm going to kick off the night by giving you an overview of the different types of earthquakes that we have here in the Pacific Northwest. And then I'm going to try to tell you a little bit about the current research that's being done into two types of these earthquakes. So I'll tell you a little bit about a project that's in its very early stages and a project that's getting towards its end. So many of you may have seen this cartoon before. So this is a figure that we show a lot because it does a nice job illustrating the tectonics of the Pacific Northwest. So the Cascadia subduction zone is a 1,000-kilometer long fault that extends from British Columbia all the way down to Northern California. And here we have the Juan de Fuca plate subducting beneath the North American plate. And we're capable of getting three different types of earthquakes in the Pacific Northwest. So the first type are crustal earthquakes. So these happen in response to crustal deformation. Some of the big ones that you might have heard of, there was a Seattle Fault earthquake sometime around the year 900 AD. There was also a large earthquake in eastern Washington in 1872. The second type of earthquake that we often talk about are these deep earthquakes. So these are earthquakes that occur in the subducting Juan de Fuca plate. And these are our most frequent types of earthquakes. So the one you might remember is the 2001 Nisqually earthquake. There was also one in 1965 and then one in 1949 before that. And then finally, the third type of earthquake that I'm going to be talking about tonight are subduction zone earthquakes. So these are earthquakes that occur when this red area, this area that's outlined in red, slips. So when the subducting Juan de Fuca plate slips past the North American plate. And these are very large earthquakes, so generally magnitude 8 or magnitude 9. And the last one of these that occurred in the Pacific Northwest happened in the year 1700. And we know that from looking at the geologic record and also from oral tribal records. Okay, so we know that the Cascadia subduction zone is capable of having these three types of earthquakes, but how frequently do they occur? So we generally think of these probabilities in terms of how likely these earthquakes are to occur in the next 50 years. So I'm in my early 30s. I often think of this as the percent chance of one of these earthquakes happening in my lifetime. So for a crustal earthquake, we generally say there's about a 15% chance of a magnitude 6.5 or above happening in the Puget Sound region. But I am going to show you a new project later that Brian Sherrod's doing that might be changing how we think about this number. Deep earthquakes, remember I said these are our most frequent, so we say that there's an 84% chance of one of these happening in the next 50 years. So they're pretty common. And finally, the subduction zone, the magnitude 9 earthquakes. So we know, again, from that geologic record that they happen roughly every 500 years or so. So we estimate that that means there's about a 14% chance of one of those happening in the next 50 years. And this is about 5,000 times larger in terms of energy release than these 6.5s. So another way to think of these earthquakes and to understand the difference between them is to look at maps of shaking that we would expect from them. So on the left, this is a shake map from the magnitude 6.8 2001 Nisqually earthquake. So this is showing you the areas in Washington that experienced shaking during that earthquake. So you can see here that a large swath of the Puget Lowland area is kind of in this orange and yellow. So that's very strong to strong ground shaking. Okay, and it affected, you can even see light shaking throughout most of Washington and northern Oregon. So if we look at, this is now a hypothetical shake map, okay? So we haven't seen a large earthquake on the Seattle Fault in our lifetime, so this is what we would estimate what it would be like. So here you see that there's stronger ground shaking along the fault, so the Seattle Fault is right about here where I'm pointing. So in that area, we experience severe to violent shaking, and then the shaking decays as you move further away. So what about one of those magnitude 9 earthquakes? So this was a deep earthquake, this was a crustal fault earthquake. How do the magnitude 9 earthquakes compare? So this is a shake map for, again, a hypothetical magnitude 9 earthquake. You can now see that this red area, so this severe, this violent shaking, is now everywhere along the coast. And that's because, remember, the Cascadia megathrust extends everywhere along the coast. And as we would expect, that shaking gets lighter as we move further inland. And so the big difference here is that this is affecting a much wider area than the other types of earthquakes. So here you're experiencing strong shaking from Canada all the way down to Northern California. Okay, so for the remainder of this talk, I'm going to show you talk to you about two projects that are trying to study crustal fault earthquakes in the Puget Sound region and magnitude 9 earthquakes on the Cascadia megathrust. So as I mentioned, these Nisqually-style earthquakes, we see them more frequently. We think we understand them a bit better. We know how to prepare for them a bit better. But for these earthquakes that we haven't seen in our lifetime, we need to we have to look for other options to learn about them. So we either need to look at the geologic record, or we need to maybe do supercomputer simulations. So I'll show you a preview of what that looks like in a minute. Okay, so first, I'm going to talk about this project that looks at shallow crustal earthquakes in the Puget Sound area. And this is work that's been done by Brian Sherrod, Richard Styron, and Stephen Angster at the USGS. So one of the goals of this study, which is still in its preliminary stages, is to constrain the earthquake recurrence and magnitude for Puget Sound area crustal earthquakes. So this is a map showing the major Puget Sound area faults, and this gray box here is meant to denote the region that they're studying. So one of the questions that they're trying to answer with this new study is, what is the estimated magnitude of previous earthquakes that have occurred in the Puget Sound region? So one of the things that they're doing is they're looking at fault offsets, so how much the fault has moved in the past. And to do this, they can dig trenches across faults, they can look at scarp profiles, and they can look at how much the paleo earthquakes uplifted shorelines. And so this can give them an idea for how much the fault moved, and a lot of the estimates that they're seeing are between 0.5 and 8 meters. So another thing that they need to look at in order to estimate the magnitude of these earthquakes is how long the fault is. So recently, we now have a lot of these beautiful LiDAR images, which are just a surveying technique that let you see the topography of the surface. And you can see here, for evidence of the Seattle fault. So you can trace these faults in the LiDAR images, and you can estimate their length. So the estimates that they're making in this project, so far they're seeing fault lengths that range from 1 to 30 kilometers in the LiDAR images, but they could be longer. Some of these fault scarps could be difficult to see. So using these two things, so how long the fault is and how much they think the fault moved, they can estimate a magnitude for what these earthquakes, how big these earthquakes were in the past. So this image might be a little bit hard to see, but this is showing magnitude on the bottom axis, and these are all different paleo earthquakes that they see in the geologic record. And where these humps are the most likely magnitude of those earthquakes. And so they're seeing magnitude estimates for earthquakes in the Puget Sound area that are between 6.4 and 7.5. Okay, so then the question becomes, how often do these earthquakes occur? And so this image here is showing earthquakes that they're finding and how many years before present those earthquakes occurred. And these are in thousands of years. So this is 2,000 years ago, 4,000 years ago, et cetera. And so these bars are color-coded. So each bar is an earthquake, and the colors are color-coded to denote which fault they occurred on. And the way to read these bars is that the center of the bar is the most likely age for the earthquake, and then the tails of the bars are possible ages, but less likely. Okay. So if we count these up, they estimate that there's been 27 of these large earthquakes in the Puget Sound area in the past 16,000 years. However, if you just look at the past 4,000 years, so this cluster right here, there's been about 21 earthquakes in the past 4,000 years. So the recurrence interval, so how frequently do these earthquakes occur over the past 16,000 years, is 400 years. But again, if we just look at this most recent segment, they're happening about roughly every 200 years. Okay, so this is how we are starting to refine those estimates for how frequently we might expect large crustal earthquakes to occur in the Puget Sound region. And I'm sure Brian will update you as this work progresses in the future. Okay, so now I'm going to finish up by telling you a little bit about a project that's a little bit further along to study Cascadia megathrust earthquakes. So these are those large earthquakes that occur along the megathrust fault offshore. So recently, we had a 6-year, $3 million collaboration between the University of Washington, which was NSF funded, and the U.S. Geological Survey. We called it the M9 project. So M9 stands for magnitude 9 earthquake. And the goal of the M9 project was to reduce the catastrophic potential of Cascadia megathrust earthquakes through advances in hazard assessment and adaptive planning. And I'll tell you what that means in a minute. So this is a schematic of our M9 project. And so my role in the project was up here. So we ran 50 different computer simulations of magnitude 9 earthquakes that could occur in the Pacific Northwest. So these are hypothetical earthquakes. And we really wanted to see the range of possibilities for different scenarios. So what is the best case scenario? What is the worst case scenario? And then we would take those supercomputer simulations and we pass them on to people who are studying tsunami generation, the impact of ground shaking on buildings and infrastructure, as well as the generation of liquefaction and landslides. And then finally, we had some social scientists on the project that are trying to understand and study how do we now present all this information to communities in a way that is useful to them. So as I mentioned, we ran 50 different supercomputer simulations of magnitude 9 earthquakes. This is an example of one of those simulations. So you see the earthquake starts here at the hypocenter. Seismic waves radiate out, so the entire megathrust is going to rupture in this scenario. Here you see shaking has arrived at Crescent City. These wiggles represent shaking. Shaking has arrived at Portland, La Grande, and Seattle. I'm going to play that one more time and point out a few things. So again, we have seismic waves radiating outwards from the hypocenter. Seismic waves are starting to reach Portland. They're just about to reach Crescent City and La Grande and Seattle. And so 2 things that I'll point out here, and then we'll talk a bit more about the detailed results. But one is that you'll notice Crescent City has much stronger shaking than some of these other areas. And that's because Crescent City's on the coast. It's a lot closer to that megathrust fault offshore, so it'll experience strong ground shaking. Now, the other interesting thing, and I'm going to talk about this in detail, you'll notice that even though Seattle and La Grande are the same distance inland, so they're the same distance away from the megathrust fault offshore, Seattle has much stronger ground shaking than La Grande. And that's because Seattle sits within a deep sedimentary basin that amplifies ground shaking. So let's chat a bit more about that. So one of the major results of this project was that local geology is going to significantly impact the strength of your ground shaking. So as I just mentioned, Seattle sits within a deep sedimentary basin. One analogy that we like to use is that this is like a bowl of Jell-O. So if you shake the bowl of Jell-O, because the Jell-O inside is so weak, it'll shake much more than the bowl or the plate that it's on. So this is just a little schematic, seismic waves entering the sedimentary basin and amplifying as they enter the basin. And it's not just the sedimentary basin, but also shallow, soft soils will also amplify your ground shaking. So both of these things matter. So this is just an example just to show you about how shallow soft soils will amplify ground shaking. So this is a figure from Kathy Troost at the University of Washington. And this map here is showing in colored areas the thickness of artificial fill or Holocene alluvium sediments. So this is very weak material. And so in addition to being in the basin and having the basin amplify your ground shaking, these areas will also have more amplification on top of that because of their shallow soft soils. Okay, so this is a geologic map of Washington, and I don't expect you to be able to see all these different things, but I just want to point out this yellow color here is sediment. So the Puget Lowland, even though not everywhere in the Puget Lowland is in a deep sedimentary basin like Seattle is, it still has some sedimentary material at the surface. And so this is going to amplify ground shaking in that entire area. So I'm going to, in a minute, zoom in on one of our supercomputer simulations in this region. But first, I just want to point out, so this is the Puget Lowland. I just said we have sedimentary material at the surface, but then we also have these deep basins. So this map here, I know it's a little hard to orient yourself. Seattle is right around here. And everywhere that you see dark blue is, or most places that you see dark blue, is a sedimentary basin. So there's a basin beneath Everett, there's a basin beneath Seattle, there's a basin beneath Tacoma. So everywhere. No. So this is one of the results from our M9 project supercomputer simulations. So this is showing long period shaking that's going to impact tall buildings. And so what I'm showing you here is shaking intensity at a period of three seconds. So this is a shaking that would impact maybe a 30-story building, so fairly long period. So everywhere you see red color is stronger shaking. Everywhere you see light color is weaker shaking. And you can see that the entire Puget Lowland is lighting up compared to areas that are not in the Puget Lowland, so areas on the Olympic Peninsula are white. And the Seattle Basin and the Tacoma Basin are lighting up even the most, and that's because of those deep sedimentary basins. Okay, so the second outcome of this magnitude 9 project is that there are a range of possibilities. Okay, so I mentioned we ran 50 different computer simulations, and there was a wide range of shaking intensities. And so part of the reason for this was because we varied a number of different rupture parameters. So when we ran these supercomputer simulations, we varied the hypocenter location, so that's where the earthquake starts. So sometimes we had it start in the north, sometimes we had it start in the south, sometimes we had it start in the middle. We also varied the inland rupture extent, so that's how close the rupture gets to Seattle. And finally, we also varied the location of these strong patches on the fault. So there's certain patches on the fault that seem to radiate the strongest ground shaking, and so their location matters. So we also varied that. So given that I don't have a ton of time, I'm just going to show you an example of what happens when we vary the hypocenter, so where the earthquake starts. And so this is the most technical I'm going to get, so bear with me for a second. But the reason why this hypocenter location matters is because of something called rupture directivity. So rupture directivity refers to a phenomena where earthquake ground shaking is strongest in the direction of fault rupture. So you can kind of think of this like a Doppler effect. You know how an ambulance sounds different when it's coming towards you versus when it's going away from you? That's similar to what's happening here. So I tried to draw you a schematic. So this black line here is a fault. And let's say the fault, an earthquake starts on the fault at this yellow star. And then I'm going to say the fault is unzipping in this direction, so towards the right. So that means that anything in front of that direction, so towards the right, will experience stronger shaking as these seismic waves pile up on their way in that direction. And areas behind the unzipping of the fault will experience weaker shaking. So let's look at two different magnitude 9 earthquake scenarios. So for scenario A, so I should explain this first. So everywhere you see color is a spot on the megathrust fault that's going to move, okay? And it's going to, the hypocenter location is where this star is. So the earthquake will start here for this scenario, and then it'll unzip in all these directions. So to the south, to the west, to the north. But you'll notice that it's going to be directed away from Seattle. So for scenario B, so this is, they're both magnitude 9 earthquakes, but in this case, the hypocenter starts pretty far offshore. So it's going, and it's also to the south. So the earthquake rupture is going to unzip to the north, to the east, and to the south. So you'll notice now that it's unzipping in the direction towards Seattle. So let's look at what the ground shaking would look like in each of these scenarios. Whoops. Okay. So this is for shaking recorded, hypothetically recorded, at a site in Seattle. So this is the velocity of the ground shaking over time. And these are both to the same scale. So both magnitude 9 earthquakes to the same scale, same location in Seattle. But you'll notice that the shaking in this scenario is about 4 times greater, just because we changed where the earthquake starts. So where the earthquake starts makes a big difference in terms of the ground shaking you might experience. So I do want to briefly touch on other parts of the project. So I did mention I'm a seismologist. I worked on these supercomputer simulations, but there are a lot of other pieces to that M9 project that are also happening. So we have some folks at the University of Washington that are now taking our hypothetical ground motions and they're putting them through their building models. This is exaggerated, just so you know. We also have people that are looking at the potential for landslides. So they look at the slopes that already exist in Seattle, and then they take into account the ground shaking that we're predicting. And everywhere you see color here, so this is West Seattle, this is where I live. So everywhere you see color, so on these steep slopes are areas where they would predict landslides to be likely. We also have people that are doing tsunami simulations. So as we know from the 2011 Tohoku earthquake and the 2004 Sumatra earthquake, the tsunami has the greatest impact on loss of life. So we also have people that are doing simulations of tsunami generation and inundation. And then finally, I did mention that we have some social scientists on the project. So they're taking some of the results. This is an example where they're taking some tsunami simulations to local communities. So this is a workshop that they had in Aberdeen, Washington, to try to show the communities these different possible outcomes and discuss community planning for future. Okay, so I'm done. I think we're going to hold questions to the end, but thank you very much.
Okay, thank you, Aaron. That was great. Aaron's going to cue up our next talk. You can probably hear me okay. Well, I'll speak into this microphone. So our next speaker is Harold Tobin. Again, he's the state seismologist. He's based at the University of Washington, and he's a geologist / geophysicist. You guys, he couldn't make his mind up. And he's based at the seismology lab at Earth and Space Sciences at UW. And I do want to mention that he's recently come to us from the University of Wisconsin, and I was teasing him earlier that he's finally come to the real UW, okay? And Harold is going to talk to us about monitoring, and including seismic monitoring in the Pacific Northwest, including the planned earthquake early warning system that they're building out here in the Northwest. Harold?
Thank you. But of course, it's not true. I came to the real UW, and the other one is UW, and that's the difference. Yeah. But yeah, I'm actually really happy to be in Seattle, and so happy that all of you have come out tonight to listen to us talk about these things. I'm going to take a step back from now that Aaron has kind of scared you about a lot of the potential scenarios, and take a big picture look at the subduction zone, and then segue that into talking about earthquake early warning, as Brian just said. So, you know, we literally inhabit the subduction zone, right? And it is the thing that makes this place a beautiful place to live. And we live in the shadow, literally sometimes, of volcanoes that are directly related to the existence of the plate tectonic system, the activity of the subduction zone. We can look out the other way from the city and see the Olympic Mountains. And if you take a perspective on the Olympics, you know, from offshore looking in towards the coastline. Actually, I got my start as a researcher in this field as an undergraduate field assistant to one of my profs, working 2 summers in the Olympics, spending 35, 40 days in the backcountry up there, high up in the mountains. Those mountains are literally there, you know, because of tens of thousands, hundreds of thousands, millions of earthquakes that have slowly uplifted them, earthquake by earthquake by earthquake. And maybe that's a daunting thought in a way, but to me it just says that we choose this place to live, or we are here in part because the earth is so alive in our region, and that's something to both embrace and recognize the natural hazard from. And when we look at a view like this, we can recognize too that the system is something that affects us on land, but has equally sort of complex and interesting geology offshore. And you look out there, and hopefully I can figure out which one of these buttons is the laser. Maybe that one, there we go. You look out there and you can see all these, maybe these sort of lines or these things that look like worms marching northward, and they're literally like the folds in the carpet, meaning the Juan de Fuca plate that's going down underneath our feet, you know, look down, 30 miles straight down, right, is that subducted thing that used to be the seafloor of the Pacific Ocean off our coast, but has transferred underneath our feet in the North American continental plate, and it folds up the layers of sediment and scrapes them off that were sitting out here on top of the subduction zone. The part that Aaron has just told you about, where the fault zone is actually underlies all of this region, mostly offshore, a little bit onshore, but an awful lot of that fault is actually the offshore part. So we literally inhabit the subduction zone. Of course, that comes with this cost, and we've already talked a little bit about these earthquakes, and the deep slab earthquakes, the ones that are down there in that chunk of the former seafloor of the Pacific Ocean that's below our feet, are the ones that we're most likely to experience in the future, as Aaron just showed you, and that we've experienced in the past. And you know, 2001 was 18 years ago, the last really strongly felt earthquake. Of course, we had a little reminder this summer. How many people were woken up by the 4.6 in Muro in July? Yeah, I was. I had just gotten off a plane in Japan for a research meeting over there, so my phone started buzzing like crazy with the news media and stuff asking me questions, and I was sort of having dinner and a beer in Japan, so I couldn't answer very, very directly. But our region is an earthquake-prone region. And so I'm going to show you just basically the summation of 40 years of the data that the Pacific Northwest Seismic Network has collected. It was actually, this beautiful visualization was created by our fantastic colleague, Nathan Becker at the Tsunami Warning Center. But it's going to show you our region. The dates are going by up here in the corner. So there's 1980. We're just going month by month. The size of the circles is scaled by how big the earthquakes are. You can see the scaling right there. Right? And then they're just going to appear, and then they're going to slowly fade away. And depth is the color. So you can see big earthquakes and little ones, and we constantly have earthquakes in our region. There are tens of thousands of earthquakes over what we call our earthquake catalog. And they also occur in patterns that we recognize as specific areas. So offshore, actually, we see a lot of earthquakes at the kind of the southern end and northern end of this Juan de Fuca plate, where it kind of meets a couple of other plates, and they're breaking up and jostling at their edges. And then we also see them along what's called the Blanco Transform Fault, a strike-slip fault, much like the San Andreas down here. Northern California, Southern Oregon had a lot pop off in the 1990s. But meanwhile, we're seeing a kind of a constant background. Of course, we don't feel the vast majority of these earthquakes that happen in the Puget Sound region. Oregon's pretty lucky. It just stays really well. Oregon's pretty boring is another way I'll put it to a seismologist. But it has a lot less going on down there. And what I'm going to do is actually jump this ahead a little bit. There's so much interesting stuff in all the time that's available. The question is, can I get the mouse to talk to me or not? Maybe I can't. Maybe I can't see it well enough to it's down there, but okay. So that was Nisqually, right? December 2001. And it's close enough now. We'll let it run out a little bit. So our main locuses of earthquakes are actually those crustal or slab earthquakes right under the Puget Sound region, and that's why a lot of the concentrated monitoring has been there. These distant offshore ones, even though they're pretty large and pretty frequent, really don't present a hazard onshore. They're not tsunami sources, and they're also too far away to create a lot of shaking onshore from these events out here. Now, notice what's missing, right? We just don't see anything in that part where Aaron just told us was the potential magnitude 9 earthquake all in that area. We see it all filling in further in underneath our feet or much further offshore, but not in the part that we think of as this critical megathrust zone. So I'll call that the dog that hasn't barked in the night, right? In the entire time we've been recording earthquakes, there's been barely anything at all, even down at low magnitude levels on the Cascadia subduction zone. Aaron already told you about the probabilities, so I won't go over that now. But we know that it is actually locked up and ready to produce the next earthquake for a number of reasons. And one is we can actually literally measure the way the strain is accumulating in the crust using very sophisticated GPS measurements and other things that tell us how the two plates are locked together. But also we know that there was this event in 1700. And if you've probably heard this story already because you're all here because you're interested at least in the earthquakes, but it's the best piece of geo-sleuthing, I think, of all time, basically, that Brian Atwater from USGS here in Seattle at UW, David Yamaguchi, Kenji Sataki, and others did together. And they knew that there were the legends from the indigenous native tribes along the coast that that big events had happened, flooding villages and strong shaking. They discovered that there were all kinds of deposits that came from the actual tsunami in the coastal regions over the top of topsoil. Suddenly, both sands that came from the tsunami and then mud on top that showed that the land had been dropped down and in fact killed all the trees all of a sudden in these ghost forests. And the tree ring dating showed not only the year that took place, but even the season, the winter time. But we know it even better than that, because the historians in Japan were aware of this tsunami that had no earthquake associated with it, the ghost tsunami or the orphan tsunami of that year, 1700. And there were lots and lots of very detailed historical accounts of the damage done by a tsunami with no known earthquake. And by computer simulations of what it would have taken to inundate the Japanese coast exactly that way, the conclusion was drawn that only a magnitude 9 earthquake coming from this portion, the Pacific Northwest region of the Northern Pacific, could have produced the tsunami that accounts for all of that. So it actually gives us the date and the time, literally down to the individual day. And any people in the room who know about this will know that I have a typo on there. I can't believe I forgot to fix that since the last time I used that slide. January 26th is the correct day, right? So our region is an earthquake region, and we know it. And so, when you think about earthquakes, they don't happen very often, so we don't think about the losses from them all that often. But this is FEMA's estimate of the annualized, meaning if you average out even things that don't happen for decades and decades, the cost associated with them, you get really significant numbers. Most of the earthquake hazard for the US is on the West Coast. A large fraction of that is in California, but something like 700 million per year when you average out earthquake losses over time is in our region up here. So we really have to be thinking about all of this and thinking about what can we do to mitigate it. And my argument, of course, as a person who works on this, is that we don't spend nearly enough money on all sorts of mitigation because the annualized costs potentially are so large. So that's led to the work of the Pacific Northwest Seismic Network. And my predecessors here, you heard I just got here a year ago, so I can't claim much credit for the PNSN. Paul Bowden, who's the network manager for PNSN, is here now. Steve Malone, who's the former director of the PNSN and was famous for warning all of you about Mount St. Helens back in 1980, did a lot to make this happen. We now have hundreds of seismic stations that are contributing data all the time, real-time data feeding into our computers, to our network at UW, and allowing us to rapidly calculate how big an earthquake was, where it's located, how it might be aligned with particular faults or parts of the plate tectonic system that we do or don't know about. And now also allows us to do this kind of not just fast, but even real-time earthquake early warning that I'll tell you about in a minute. And our hosts tonight, the USGS, are our big funding source at UW, so we can operate this seismic network. We're in our 50-year anniversary right now in 2019. So our mission is reducing the impacts of earthquakes and eruptions by providing the information, and that's one component of that is what we're doing right now, right? And our job is also to monitor ground motions, and ultimately now a big thing that's become kind of the exciting new thing, and also the big activity for us in recent years and right now, is operating this Shake Alert earthquake early warning system. So I'll talk a little bit about what earthquakes are, because to understand earthquake early warning, we have to think about this. We experience an earthquake as shaking, right? The ground is shaking for us, and that's what we feel. But the earthquake itself, as Aaron just kind of really made very obvious, is the slip that happens on the fault. So as the two sides of the fault that are storing up that strain, they're frictionally stuck together, just like if you have a heavy piece of furniture that you can't push across the floor because of the friction holding it down to the floor. But when the stresses that accumulate from plate tectonics, from the push of the plates, overcomes that, it breaks, and it slips along this kind of rough surface. It's really hard to point from these high angles over here, or maybe the pointer's just dying on me, but it slips along that rough surface, and as it chatters along, it's radiating those seismic waves, just like noise, when you push that piece of furniture and something goes across the floor. The seismic waves are something like that. Unlike sound waves, seismic waves radiate in a couple of different modes. And so there's what we call the P waves and the S waves, P for primary or first, and S for secondary, and then the surface waves that follow them, and this thing called PGA means peak ground acceleration, so the part of the shaking that has the highest amplitude and does the most damage. The key thing for us that we'll see in a few minutes is that those P waves come first, and they tend not to be damaging, but they get to a sensor very quickly, and they're followed by these much slower but more damaging waves that come later. All right, so zooming back out, then we can say, well, these subduction zones are not just the Pacific Northwest. There are actually lots of places around the world. That's a partial list. And they all share some common features. So now we kind of understand that that plate that's coming in is going down beneath our feet. Eventually, when it gets quite deep, it's so deep that it starts the melting process that fuels our volcanoes. So, you know, we have the subduction process to thank for all of the volcanoes that we enjoy being near, and also worry about a different hazard we're not talking about tonight, right? But the part that's shallower is not so hot, and so it's colder, and that's where the plates can get stuck together and ultimately create that earthquake that then ruptures out and along the subduction zone, and crucially, takes this portion that was stuck together and sort of pulled back, almost like an archer pulling a bow back, for the hundreds of years in between earthquakes, right? Accumulating that strain at a rate of just a couple of inches a year, about the rate your fingernails grow is a way to think about it. So let your fingernails grow for 300, 400 years, and you've got many, many tens of feet, you know, dozens of feet of accumulated missing slip, and all of a sudden that goes. And when that displaces the sea bottom, it also is the thing that launches the tsunami. That pushes the water up in exactly the same way it pushes the sea bottom up, and then the tsunami goes. So that's the Geology 101 portion of this evening, right there is the diagram. The uplift of the seabed is the cause of the tsunami. And we know, of course, that for subduction zone earthquakes in our experience, the tsunamis are almost always actually, when they're generated at least, the largest hazard from the subduction earthquake. And that was probably true in 1700 for the people who lived along the coast. That's a photo from Tohoku, Japan in March 2011 during that very large tsunami. And it was a shocking moment for all of us, right? Seeing all that stuff, especially the live footage that was coming in on television and everything at that time. But I want to not just say these events are so overwhelming, and I think a lot of people who read that New Yorker article just thought they're so overwhelming, there's nothing we can do about them, everything's gone, everything west of I-5 will be toast, is the quote from the New Yorker article. And it's actually kind of a missed quote anyway, because what FEMA was really trying to say was we have to plan as if everything west of I-5 could be toast, or anything west of I-5, and they didn't even mean I-5, they really meant west of the Puget Sound, Puget Lowlands region. But you know, to think about how all of this happens is to recognize that in this disaster, which was one of the hugest subduction zone earthquake disasters, 19,000 people lost their lives, virtually all of them, by the way, from the tsunami and not from the earthquake. And that's partly because of excellent preparedness in Japan, building codes, and life safety structures. So earthquakes, subduction zone earthquakes, are eminently survivable, right? And even the tsunami, you can look at it a couple of different ways. 19,000 people lost their lives. At the moment of the earthquake, 350,000 people were in the death zone of the tsunami. So that means 94% of the people escaped and 6% were killed. It's a terrible disaster, and I wouldn't want to minimize that at all. But again, it means that these things are things we can prepare for and are potentially very survivable for the vast majority of us. The potential loss of life in a Cascadia scenario, even in some of the worst case scenarios, is only a very, very tiny fraction of the population. Many of us will be very inconvenienced by the damage that comes from the earthquake, but I don't want people to think of it as something that's not worth thinking too hard about. So, in the frame of talking about things that we're thinking about then, one, and it's one of many ways to prepare for earthquakes, and we're going to hear a lot from the next two speakers about other forms of preparation, but one is we've recognized through the USGS and its university partners, which includes us, but also Oregon, Berkeley, and Caltech, that there's a capability, a technological capability to warn people before the shaking gets to them in many, many cases for earthquakes, and for tsunamis for that matter, and that we can use that information to help protect people and save lives. So that's led to this system called Shake Alert, Earthquake Early Warning. And it takes advantage of the fact that there are all of these seismic stations. Ours are these pink ones up here at the PNS end, but then California is loaded with them as well, of course. And there's even a little bit of offshore instrumentation. And use all of those stations to detect those P waves and warn people before those damaging S waves get to them. I'll show a little animation of that in a second. So actually, Shake Alert is here in the sense that we are already operating the system. We're using it in a pilot mode now, even in our region, and have some pilot infrastructure collaborators who are using it to do real things to protect infrastructure now. And full-scale public alerting, meaning via an alert that would come to your phone through the WIA system, the like Amber Alert style system, or an app, just went live in California 2 weeks ago. There's Governor Newsom announcing it. And we're moving to public alerting in Washington and probably in Oregon in October 2020 is the goal that the State Emergency Management Division has set out and that we're full partners on with that. So there are some of the examples, the direct emergency alerts, which are now potentially taking place. That's the way everybody thinks of it potentially happening. There's two issues with those direct emergency alerts. One is that they only can show you a very simple message. The technology is just a text message like this. And the second is that because of just design of that system, and actually in part for some very good reasons, there are built-in latencies and delays that are hard to overcome. It's no big deal for an Amber Alert to have it get to your phone 20 or 30 seconds after the alert. But for an earthquake, that could be getting the alert after the earthquake hits you instead of before the earthquake hits you. So people are working hard on that problem, but also working on releasing these apps that you instead download, which have at least the promise of reducing some of that latency and giving us more information during and after, crucially after the earthquake, like Shake Alert LA and this other one up here called MyShake. All right, so how does earthquake early warning really work? And the key thing is that it's not prediction of the earthquake. It's detecting the earthquake as soon as it happens. So there's the earthquake in the subsurface. It starts radiating waves. Those first ones are the P waves. The red, pink ones behind them are the S waves. So the P waves start passing some of the seismic stations, which can then immediately transfer their information over our telemeter data or our internet connections back to UW or the other centers within approximately, numbers like a couple of seconds. The location of the earthquake and a rough estimate of the initial magnitude is done, and then it's determined whether an alert should be sent out. You beam the alert out, and then, hopefully that doesn't happen, but at least not quite like that, but before the damaging waves get there. So that's the fundamental principle behind it. We've got lots of examples of ones that have been caught during our whole development and testing phase. This is just one where an earthquake took place up there by Astoria, and there was a first alert issued just a few seconds after, less than 2 seconds following the P wave arrival to the surface, and so that left 24 seconds to warn people in the Portland region of a potential earthquake. The Monroe earthquake was close to Seattle. That was a tougher one to do with a lot of advance warning, but our system generated a warning with about, I think it's 8.5 seconds of potential advance warning. Not a lot of time, but enough time to mentally prepare and do some of your activities like drop cover and hold on, and I'll show you something interesting about that in just a second. Here's another rupture simulation for a magnitude 9 earthquake by a different group using some of the same kinds of simulations that Aaron just showed you at San Diego State. It's again showing you a big magnitude 9 earthquake, and you can actually see the effects of the directivity that you all are experts on now that Aaron just showed us, as well as some of the concentration of seismic waves in the softer rock offshore. But if you look at the time scale, I know it's tiny down here, 2 minutes have already passed since the earthquake started, and by the time the waves get to Seattle, it's going to be more on the order of 3 minutes plus down here on this time scale. And so what it suggests is that for at least some of those scenarios, there's a potential to detect it as soon as the waves come ashore, and then still have significantly longer amounts of lead time in the Puget Sound region. If it's closer and directly offshore, then it's more like in the 30 to 40 seconds or 40 to 50 seconds kind of time frame, but still significant amounts of time. So different earthquakes give us different responses.
Much more similar to the Mexican
I wanted to show you this video. I was actually a graduate student
5:04
doing
p.m.
this
Latin
kind of
American
science
Studies
at
1
UC
was
Santa
underway
Cruz.
at UC
I'd
Santa
been in
Cruz.
grad school 3 weeks, the moment of the Loma Prieta earthquake 30 years ago. And here's a classroom. I was probably just about 2 blocks away from this classroom. Students just figured out the earthquake was happening. They didn't drop cover and hold on, did they? Everybody got up. Stuff is all falling from the ceiling. Nobody should get in a doorway during an earthquake, and nobody should try to exit the room. It's the falling stuff that's gonna hurt you or injure you during an
With
earthquake.
video cameras
And there are a couple
everywhere,
more of these. This was the
this
first
was the
earthquake
most
where we had
visible
lots of
earthquake
security
ever.
cam footage and all of this kind of real time, real data showing what it was like during the earthquake. Poor kid, I know. And then, of course, we all know it as the World Series earthquake, and the TV ended, and that was what a lot of people heard. Now, I was right on top of that earthquake, and the power was out, and we didn't even know how large an earthquake it was till somebody came by in a car with the radio and said the Bay Bridge just collapsed, and that was the realization. So I just showed you some really graphic examples. Falling hazards. Whoops. Let me go back there. Are very. I went the wrong way. It doesn't want to go back. There we go. And the injuries are linked to falls, and the same goes for the Northridge 1994 earthquake. So. The cost is really high, and even just being able to prevent a significant fraction of those, there's an opportunity to really save a lot. So just as a contrast, this is Anchorage. There was no earthquake early warning. Watch from when these kids notice the earthquake is starting. They're all under the desk within less than 4 seconds when that earthquake started. So most of them are trained as well in the last school, but having that early warning actually puts your brain instead of freezing to do what you're actually supposed to do. Automated control of systems. I'll skip over that. I do want to kind of talk about this just a little bit. Shake Alert Earthquake Early Warning System is an expensive thing, putting all of this together. There's an estimate that the capital investment to make it is about $40 million total, but it'll still cost us about $28 million to operate it annually. So I think in our region, it's good to put that in some units that we can actually relate to, because big numbers, $28 million sounds like a lot of money, right? But let's think about, something useful to the city of Seattle. And so I like to define a unit as 1 Wilson. Famously, he makes $35 million a year to play football now. So the cost is about 0.8 Wilson units per year, right? Not bad. Okay, the last thing I'll talk about, just if you bear with me for 2 slides, is to say that the final frontier for us is really moving offshore. The locked up fault zone is out there. Our sensors are all on land. That's not good. That's like sort of, the light is over here, but I lost my keys over there, so how do I look for my keys? So there are already some offshore scientific sensor cables that exist both in Canada and in the US, and there are a few of those seismometers that are starting to be on the seafloor that can feed data back, but we need a lot more of that kind of information, and there's been a lot of work go into trying to determine what sort of earthquake early warning we could do. And we're looking right now at adding a lot of seismic detection systems and other things to this region off Oregon where the cable already exists. We'd love to see that go a lot further. So just to sum up, they're a real concern, right? But we prepare, not despair. I think that's one of my key messages. And early warning is on the cusp of reality here, and we want to integrate it. And it's an and, not an or, right? An and, not an or with regard to other resilience efforts. This doesn't replace preparedness. Thanks very much.
Thank you, Harold. That was really good. Thank you very much. So again, we're going to do questions at the end. And Aaron is going to cue up our next talk. So our next speaker is John Hooper. And John is a senior principal and director of earthquake engineering at Magnuson Klemensic Associates here in Seattle. We've had a long working relationship with John, probably 25 years now, and he takes our stuff and really puts it into action, and puts it to use, and puts it into designs of buildings here that we live in and work in every day. And so his work is extremely important, very valuable. And so John is going to talk to us about the engineering and the built environment here in the Pacific Northwest.
Thank you. Appreciate it. Pleasure to be here. Thank you for that. And built environment relative to earthquakes, because that's what we're talking about here tonight. And actually, we go back over 30 years, back to 1988, when I first met Brian Atwater when he described to me the subduction zone earthquake, for which I didn't believe him for about a year or two. He convinced me at the very end. What I want to talk to you, though, is about the history of code development, kind of give you a sense of our building stock here in the Puget Sound area and what you can expect from it. Not just brand new towers that have been designed in the last 5 to 10 years, but the stuff that's been around here for over 100 years. And we've been trying to deal with this phenomenon of earthquakes for about this 100-year time frame. What we're trying to do is provide guidance for engineers like me and others in the Puget Sound area to design projects that are simple, economical, and reliable to protect life safety, to protect us as individuals. Property is on there, but property isn't our major focus at this time. It hasn't been easy to make these changes because we have to wait, generally speaking, for the most part of this 100 years, for earthquakes to tell us what works and what doesn't. So you have to learn from that, because Mother Nature is the best teacher of all. And it's not even close to perfect yet. We heard about this new information about the crustal events that I just heard for the first time tonight. The magnitude's a lot higher. I've heard about it before, but the magnitude's higher, and the turn period is shorter. That changes the dynamic of what we should do in building design. So I'm going to take a kind of a walk through earthquake engineering history and what we've learned. And by and large, the majority of what we learned is from California. Don't despair. California is a good state. We like them. They're good. But we work hand in hand with the state of California. And so what they learn in California, we use here in the Puget Sound area. So these lessons are very germane to what we do. We all heard about the 1906 San Francisco earthquake. Interestingly enough, nothing became of it in the design of buildings in San Francisco following that event. Missed opportunity. They may have been working on it, but nothing really happened until 1927. That was the first building code that was formulated that governed design of buildings mainly in the western United States. And within that document, they did have earthquake information and requirements, but in what is called a non-mandatory appendix, meaning you could do it or not. It depended on you, the engineer, or the jurisdiction that was adopting this building code for use of designing and constructing buildings. But if you did do it, and you did know you had earthquakes, you see the word in there, earthquake shaking is moot, meaning if it happens, you should design for it. And they gave some information to the engineering colleagues back in the time of what to do. But again, it wasn't uniformly done throughout the western United States back in 27. The next big event that really changed a lot is the 1933 Long Beach earthquake. It made a lot of changes in California that permeated its way up here very quickly. They made a bunch of legal changes, and they're called the Field Act in California, very famous for them. It banned unreinforced masonry buildings. Those unreinforced masonry buildings still exist in the Puget Sound area. You see a lot of them in small towns around us, a lot in Pioneer Square. We adopted that same ban, not in 1933, but by the 1940s, we said you can't build out of this material because you see responsive buildings like that. They also did something called a Riley Act, which basically said we need a design for earthquakes to a certain amount of force, how much the earthquake is going to try to push your building sideways due to the ground shaking underneath it. And so that was developed back in 1933. We still use that same number today throughout the United States. Interesting that we use the same minimum force. It can't be anything less than this in any building design anywhere in high seismic. And as you know now, we are high seismic. The next seminal event was the 1971 San Fernando earthquake. So remember, you saw other pointing out to the events that we had here in the Puget Sound area, the 49 and the 65. We were very clearly understanding that we had earthquakes happening here. We knew they were probably different than California because we can't see something called the San Andreas Fault, which you can actually see and walk over, so that we were doing the right things consistent with California. So when this happened, we knew that this kind of thing would be expected up here in the Puget Sound area as well. What did we learn? Pretty simple. Don't build on a fault. Two things happened. They created the Alquist-Priola Act in California, which mandated that you could not build on the fault. And the building code itself, about 25 years later, did the same thing. If you have a fault and you know it, some of these faults are hidden faults, so you don't necessarily know where they're at, you can't build there. Walls must be tied to the roofs and the floors. Boy, that sounds like a good idea. Why would you stack a bunch of walls and put a bit of roof on it so they could just fall right off? It makes no sense. We were doing that back in the 60s and 50s and beforehand. Yeah, all right. We learned the lesson the hard way. There's a term I want to talk to you about called non-ductile concrete. This is concrete buildings that don't have sufficient amount of reinforcing steel within them and the right orientation of that reinforcing steel. It's from this earthquake that we really started pushing the fact that concrete itself is not a bad material. It's its interaction with the reinforcing steel that is inside of it and how it all connects together wasn't being done very well. And so if you think about that, by the mid-1970s, we think we kind of solved the problem. We never really solved what we think we do. Anything built before then that's concrete, maybe not a good thing. Maybe not a good thing. And finally, some structures are more important than others. What that means is we understood that if you're a hospital, your design objective for seismic performance should be higher because that's where people go when they're hurt versus just a residence. You could argue that shouldn't be the case, but we separated performance between what we call essential facilities and ordinary occupancies like we are in here today. 1985, Mexico City, big buildings fell down. 15 to 20-story buildings fell down like this, the Pino Suarez. This is a detail for the really engineering nerdy guys and gals in the audience. Steel columns collapsed because they weren't strong enough. And so we fixed that in the building code so that we don't have that problem anymore. Again, Mother Nature is really describing what we should do, and she tells it to us very well. And buildings that are next to each other, that can be a problem. They pound, they hit, and they cause damage and potentially collapse where they hit together. And we've changed our requirements because of this earthquake, how far apart or how close two buildings can be built to each other. Before that time, we didn't have rules for that. So if you think about buildings around here that are really close together, as you walk by them, think about that. Or not, it's your choice. I think about it way too much, obviously. The 1994 Northridge earthquake, it showed us the best system that we thought we knew about was what we call steel frames. They cracked. Steel can crack. This is about this pointer's not working anymore, it doesn't look like. That flange, you see right here, that's 3 inches thick of solid steel, cracked wide open. And that happened in numerous buildings in this earthquake. So we had to develop a whole new way to doing steel buildings. And then, so anything built before 1994 has potential for looking like that. This is a tougher slide to see. These are what we call tilt-up buildings. They are basically concrete wall buildings that they actually build a concrete on the ground and they tilt them up. And they make warehouses out of them. Think about the Kent Valley and all those warehouses like that. Before 1994, the separation between those walls and roofs, they separated way too much, and we lost 200 of them in that earthquake. So we improved that connection to make them stronger than we had previously to help mitigate that from happening. So that's kind of the history lesson through time that I just picked the top 4 or 5 events. I want to really emphasize what we've already heard tonight and what benefits we've had this interaction with the USGS over this time frame. You've seen this slide before. I want to say what this means to the engineering in the built environment. Well, we recognized a cascade subduction zone in the late 1980s. Again, Brian Atwater came and the USGS colleagues to the Structural Engineers Association of Washington says, I think we have a problem. And we sat down for several years and tried to figure out how big of a problem it was. And by about 1992, we changed our building codes to account for this shaking, a collaboration that goes back to that time frame. Recognition of the Seattle fault, we knew that we had shallow crustal faults, but we didn't really know the size and the recurrence, et cetera. We now know it's even worse, thanks to the research that's going on at the USGS. Thank you, Brian. I don't want to talk to him anymore. And so, again, that will change what we do in the future. It'll take some time. It'll take 5 or 8 years. It doesn't happen overnight, but it's good to have this collaboration to help solve these problems together. And then finally, the recognition of the Seattle Basin. You saw the examples that Aaron showed about those simulations. We knew about them, but probably a little bit before this. We started incorporating them into our tall building designs about 2010. Not exactly the way it's being done now, but we recognize it, we try to think about it and try to make sure our tall buildings accounted for this in some degree. And I'll show you a little video here at the end of the session tonight. I do want to talk about the fact that when we design buildings, I'm not sure you're aware of this, that we have to follow building codes and standards. The building code is adopted by the state of Washington, for instance. It becomes law. It's something we engineers have to follow. Within that, though, the actual criteria for earthquakes comes in what the standard is called, this green, the SEAC book, let's call it the SEAC colored book, ASE 7-16. That tells us how to design for earthquakes in there. And what it basically does, it talks about how strong the building needs to be. Remember that 3% is a minimum. That still, again, is in this document. And how stiff it is. I mean, how much earthquake can cause a building to sway. We want to make sure it doesn't sway too much. It also tells about how to connect the pieces together, how to connect the vertical columns and horizontal beams so that they will work together and perform a robust system that can absorb the earthquake energy. And finally, it provides requirements for non-structural components. You saw in the videos that the stuff above you, in every room I go into, I never, ever sit underneath a chandelier. Why? You saw the videos. But we do have requirements for that as well, so to try to minimize, it doesn't do it perfectly, that damage that caused from non-structural components falling all around us. Within that, though, I want to describe our objective performance. What are we looking at when these different earthquakes occur? So I want to describe to you our performance objectives and performance level. I'll start with a cartoon series. We're in this building here today, and it's operational. And this is what we expect 99.99% of the time a building performs like this. But the earth starts to shake, things can go wrong, and things can happen. The next performance level we think about as engineers is called immediate occupancy. It's a performance level such that we're still sitting in here. There may be some ceiling tiles falling down. We may have lost the lights for a little bit, but we can get back in and use that facility quite handily. What we target, though, is something we call life safety. After a major event, we want people not to die and not to be seriously injured if we can help it. But in doing so, damage occurs to the structure. Not just the non-structural components you saw in those videos, but to the structural elements that are designed to support the building and absorb the energy. And finally, if the very rare event comes, the very, very rare event, we don't want the building to collapse. We want a very low likelihood of collapse. That's when the major deaths occur from the shaking hazard when that last little graphic occurs. Let's look at this with real pictures from real earthquakes. What does this look like? This is from the 1999 Chi-Chi earthquake in Taiwan. These buildings are being occupied immediately after the event, being used and occupied and people living there. Right next door to both these buildings are buildings that absolutely collapsed. Okay, so you can see in one slide, immediate occupancy versus collapse on the same slide. That's a graphical representation of a picture of real buildings. Here are visual of buildings at our life safe level. The structural elements that are designed, again, to support the building and absorb that energy, those elements do get damaged. This building is safe. Nobody dies in this building or even gets injured. But then the repair costs could be large and may not be economical to repair at all. You go a couple blocks away, you see buildings like this that are teetering on the brink. They didn't collapse. This is collapse prevention. But you can see they needed to brace this building here in the corner to make sure that it didn't fall over in an aftershock. So that's the cartoon version, real pictures, hopefully providing an image of what we do, of what the performance levels look like. What are we suggesting in the code that we are delivering, or we're attempting to deliver? I'm going to present to you what we call a seismic performance matrix. It sounds like an engineering term, right? It's just a table of information and definitions. On the one side, we talk about the ground motion levels. The amount of shaking matters. We talk about the frequent shaking at the top. That's the earthquake that occurs about every 25 to 50 years. That's the Nisqually type of earthquake for us here. That's that one. The next one is the design earthquake. That's the earthquake we designed for in the building code itself. That's the one we target as our performance. And the last one, and that occurs about every 300 to 600 years, depending on what part of the country you're in. For us, it's about 600 years. And then the last one is a maximum considered earthquake. We define it as that because that's the maximum one we want to consider because Mother Nature knows no bounds. We want to kind of do something that seems reasonable. For us, that's about a 2,000-year return period event, not in our lifetimes. What kind of performance? We take those same performance levels I just showed you operational, immediate occupancy, life safety, and collapse prevention, and we marry the two together and describe with a line what we are trying to achieve. So for a standard building, a standard brand new building, and you could think about all those brand new buildings in downtown Seattle that have been built in the last 10 years, that given that design earthquake, that dot in the middle says we want to be life safe. That event that occurs about every 600 years, it's life safe. Given that very rare event, that 2,000-year event here in Seattle, we don't want the building to collapse or has a very low likelihood of collapse. And then I also have in the slide called what we call a basic retrofit objective. We do the same things when we fix up existing buildings. I'm not sure you're aware that you're in a building that's been retrofitted. Our company had the pleasure of retrofitting this building to that performance level. So we should be okay. I'm not guaranteeing a darn thing. As I mentioned before, though, we look at essential facilities or these other buildings occupancies differently because we as society need them to a higher level, like hospitals, EOCs, police stations. Those essential facilities, we design them to a higher level of performance. Given that design earthquake, we shoot for immediate occupancy, and for that very rare event, we shoot for life safety for their performance. So I just want to emphasize that we don't earthquake-proof anything. Damage will occur. We try to control the damage by the way we design our buildings. So I want to go through and kind of uncover, if you look at a building, what is inside the building that guys like John Hooper cares about that helps protect the lives of people. I'm going to show you the systems that are typically used that support a building during earthquakes. I'm going to go through a handful of them. This is what we call a steel moment frame. This is the one that performed badly in 1994. Luckily, this was built after 1994. This is a building in Seattle that our firm designed. But those horizontal beams, those vertical columns, those combinations are what is designed to absorb the energy from the earthquake and keep the building from coming down. You can take a steel building and put these braces in them, these little cross braces. You see them everywhere along here. Again, these are all Seattle buildings. And those braces, those X braces, absorb that energy. And that's another one of our systems that we use quite a bit. Just so you know, there's over 80 systems we can choose from. I'm not going to show you all 80. I will be here all night. I'm going to show you my top 5. This is a concrete moment frame. This happens to be in Bellevue. It's similar to steel, but it's made out of concrete and a whole bunch of really, really important reinforcing steel within the concrete to do the work and protect the building from swaying back and forth too much. Some may recognize this building in Bellevue. This is exterior concrete shear walls. Those are all thick walls with a lot of reinforcing steel, and that is designed to do the work to protect the building. Over the last 15 years, nearly every tall building you see in downtown Seattle or Bellevue is made out of this, or made out of this, supported by this. If you unpeel the exterior of the building, concrete core walls, they are very robust. It's the combination of the beams. The pointer doesn't work anymore. Combination of these beams and these walls together are what protects the building. And there's a lot of reinforcing steel. If you ever had a chance to walk by one of those sites, you saw something, you probably couldn't even see through the reinforcing steel, it was so dense. And finally, where most of us live in houses, hopefully. What's there is just a plywood. This happens to be my beach cabin. And I made sure I had a lot of plywood. I wanted to make this one to make it as robust as I went. But that's the type of material that's used in probably 90% of the buildings that get built anywhere in the United States is built like this. And the plywood you see there, all the walls are what is there to resist that. And I also want to reemphasize non-structural performance. It accounts for over 70% of the earthquake losses. Might be close to 80%. But critical systems are designed to a higher standards, like the sprinkler systems and egress stairs, so that the fire can't burn it down. We learned that in 1906. And also that you can get out of the building safely. We designed that for a higher standard. I want to show you, though, the technology has changed dramatically for us. Here is a tall building, the tallest building in San Francisco. This approach we use to simulate earthquakes. We take the earthquakes from Aaron, and then we simulate our system. And then we see, and this is over-exaggerated, people. This is moving a lot more than it should. We look and make sure that the building is robust enough to take this level of shaking. And this happens to be magnitude 8 on the San Andreas Fault. In Seattle, we use a magnitude 9 on the Cascadia to make sure that the components that are supposed to resist that earthquake energy can do so. So that's the technology that has come a long ways for us. Again, exaggeration, people, exaggerations. Exaggerations. I'd like to close with this. The future efforts, I think we're in a long ways to doing the life safety pretty well. I hope we are, and hope Mother Nature doesn't surprise us too much next time. What are we doing to help improve resiliency in earthquake engineering and design? We want to look beyond life safety and collapse prevention. That's necessary, but not sufficient. What we're trying to do is estimate, given our current designs for life safety and collapse prevention, how long it takes for the building to get repaired and back to use, what we call functional recovery, after, let's say, a 500-year event. Once we understand how long that is, and we don't like the answer, we can start to provide new ideas, design, and construction strategies to reduce that, so that we can get back into our buildings instead of 2 months, 5 days, or something like that. So we're looking at that as a whole new paradigm shift, because I think we as society want and should be doing more. With that, I'll close.
That was wonderful. Yeah, thank you very much. That was great. So our final speaker tonight is Barb Graff. And I first met Barb back in, I think, 2000 when she worked as the emergency management director for the city of Bellevue. She is now the director of the Seattle Office of Emergency Management. And she's going to talk to us tonight about emergency preparedness. So,
Thanks, Brian.
thank you there.
I'll use this one. Give me that back. This is great news. I'm enjoying being here tonight because ordinarily I am the most depressing speaker of the night. Aaron had me 5 minutes in, and just if you stayed awake for Harold, everything I had to say is good news compared to everything they had to share with you. So this is fabulous. So just FYI, I want you to be aware of the fact that emergency managers all around the world, and very much so here in Seattle, are utterly best friends with our scientists, with Joan and Brian and Art and Aaron and Harold and Steve and Brian and everyone else. We believe what they say, and I'd like to share a little bit with you about what it is that we've been doing with their information as a result. First, we're trying to humanize and personalize that risk information that they spent a lot of time and a lot of really good study on. We created a hazard map that we put on our website, so you can click on your home address or your kid's school or your doctor's office or your mother's house to find out, is it in a floodplain? Is it built on soil that could potentially liquefy? Is it a building that, as far as we know, is an unreinforced masonry building? The more you know and personalize the risk, the more you're actually likely to do something about that. I'm going to talk real briefly about the kinds of things that the City of Seattle, as a representative city, has done with this risk information. One, we plan our hearts out. In the city of Seattle alone, go to our webpage, seattle.gov/emergency. You'll find a comprehensive emergency management plan, an emergency operations plan, a recovery framework, all hazards mitigation plan. You'll find continuity of plans, continuity of government plans, continuity of operations plans, incident-specific plans, including an earthquake response plan. You'll find all kinds of things that have pre-staged what our intentions are in any kind of an incident. Additionally, we have partnered with an interesting startup company called One Concern to model at a much more granular block level what are the kinds of damage we might expect to see. How many people of different ethnicities and languages and income levels live in each one of those blocks that we need to plan better for. And we also have just recently, relatively recently, finished up a seismic study of the entire water supply system for the city of Seattle. Next, we train. So there's 250 people from our 30 city departments who get trained on a regular basis in what their role is in an activated emergency operations center in order to provide response and relief to our community in any kind of a hazard, but especially an earthquake. We spend 85% of our time focused on earthquakes, because you focus on that and you're kind of covering almost everything else on your bad day list. We participate in exercises. We don't wait for the earthquake. Like you heard earlier, it's like John said, it's tough to wait to see if your best assumptions were good assumptions waiting for the earthquake to happen. So we actually design exercises to stress the plans that we built and trained on to find out how can we improve them. We also send people around the country and around the world to help in different disaster situations because they come back better inspired with good ideas to improve our plans. There's a number of projects that we have spent a lot of funding on here in the Northwest. And so I want you to be aware of that. Some of those are, we have finally torn down the viaduct instead of waiting for the earthquake and 2 sneezes to take it down for us. Yes, we got it done. Thank you very much. The tunnel has opened up. Yay, we're making our way along. We have completely redone the Elliott Bay seawall. We'd like separation between water and land. We rebuilt from scratch in a new location, Seattle City Hall. These are some of the essential buildings that John was referring to because of the services they need to provide. New City Hall, the Justice Center, the fire department and water department, training center, and the fire alarm center, so we can still take 911 calls and dispatch appropriately. Additionally, we used to have located in the Seattle Municipal Tower our main data center with all of our critical operations on floor 22, and we were finally embarrassed enough to face that. We've now relocated and made 2 redundant centers outside of any kind of high-rise or area of danger. Additionally, and I give credit to this to Mayor Nichols, who when he visited Kobe, Japan in 1995, after their earthquake, he came back with fire in his belly and recommended to the citizens of Seattle, let's do more for public safety, especially in the earthquake arena. We've now seismically retrofit all of our fire stations so that the units and the firefighters can actually get out and do some good. We hardened the water hydrants so they can draw water more reliably. We built the city's emergency operations center that we now occupy. We cached stores of emergency congregate care supply materials so that we can take care of at least 4,000 people right off the bat in different areas of the town, and many other things in order to get ourselves much better prepared. Additionally, our community centers, our parks and recreation centers, are those facilities we would use for mass care and congregate sheltering, and we've taken the time, trouble, and expense to make sure that they have been seismically mitigated so we can use them for that purpose. For the top tier, the highest capacity community centers, we've also installed permanent generators, and we have a fleet of generators that can be rolled around to other critical facilities depending on what their function is. One of the top dangers right after the shaking of an earthquake is the exposure of fire, and given the fact that your fire suppression systems could easily be damaged, et cetera, we went ahead and installed automatic gas shutoff valves at 35 of the city's most critical facilities, so that at a certain calibrated level, and this isn't just a heavy truck passing by, but the natural gas will automatically be shut off so that we're protecting from a secondary danger that hasn't yet even happened. John touched a little on unreinforced masonry. I could talk about this one for 4 hours, and you'll be glad to know that I'm not going to. But the good news is, for at least the last 7 years, the city has been trying to figure out how to be the first city outside the state of California to mandate seismic retrofit of the 1,145 buildings that make up our unreinforced masonry inventory, and we're gonna get there. This afternoon, I was just in another meeting in the mayor's office about how do we weave together the financial incentives that help not displace the low income, the minority populations, and the historically significant buildings that we don't want to lose in our next earthquake. This is not an easy thing to do. This is about a $1.2 billion proposition. And unlike the other billions of dollars of investments I showed you that the city made with tax dollars, that's $1.2 billion on private property owners. So we're trying to be sensitive about the way we did this. We tried it in the early 1970s, and then following the 1965 earthquake. Earthquakes are great motivation, but it doesn't last long. And so we passed an ordinance, and within 4 years had repealed it because we hadn't not been thoughtful enough about how to make sure we could put a retrofit ordinance in that would address this. But 33,000 people at any given time, any day, are living, sleeping, working, or dropping their kids off at a school that is an unreinforced masonry building. So we've been in a very close-knit tie with Portland for a number of years, trying to shame each other into seeing who's going to be first at this. I guarantee you Seattle's going to be first to get around to this one. Town Hall, John stole the thunder. It's seismically retrofit, so give yourselves a hand. You're in a safe building. No hurry to get out. Bars open as soon as I'm finished here. But in addition to that, in addition to Town Hall itself, we have since 1997 been teaching classes to people who live in the community whose single-family wood structures are not adequately secured to their foundation because they were built to a previous older building code. And so we started a program called Project Impact way back in the mid to late 90s, where we teach people, here's how you can do the work for yourself, if you're willing to do that. We have 2 community groups who actually loan you the tools to do it if you don't want to buy the tools. We teach contractors, and since 1997, we continue to teach those classes into 2019, and they continue to be standing room only. So I'm so impressed about the investment people living here in the community themselves are making in disaster preparedness. But in reality, with all that investment that we've made, it's still going to be a horrible day. And so the most important thing to remember is, this is where I do get as depressing as all my remaining colleagues, what you need to remember is the just-in-time delivery, including just-in-time delivery of your dinner, things just aren't going to be normal for us for quite some time. We have hundreds of bridges in our city alone, let alone the thousands that connect us to the rest of the world. With so many different important enterprises, including hospitals that count on just-in-time delivery of services, this is going to be urban camping for a certain amount of time. And so we're trying to encourage people to personalize this risk and say, you need to do something about this at the household level, the way your city has been doing it with public buildings in it, as well. Toward that, we teach more than 10,000 people annually in person, not to mention all the people we try to reach with TV programming, with our websites, we have our volunteers here tonight. Say hi to Cindy and Ann and others on your way out. They're doing an absolutely fabulous job. We hire people who are culturally competent and fluent in a language other than English to teach the classes on our behalf in order to get to especially immigrant and refugee communities who don't necessarily trust the government. Quite frankly, you don't have to be an immigrant or refugee to not trust your government these days. I need to change that to as I do that. We have been encouraging people to sign up for a program that we have called Alert Seattle. You won't need this to find out about the earthquake, as Harold mentioned. Earthquake early warnings on its way. But when we can send you information about specific areas of damage, a utility disruption, a traffic disruption, a law enforcement activity going on in the area, sign up at alert.seattle.gov so we can push that information to you. And then finally, and we've got these brochures over on the table, it is all about preparedness. And so a lot of people think about gathering their supplies. Great. A lot of people think about putting a good plan together, who's going to contact the kids and out-of-area phone contact. Great. But I'll tell you, I'm absolutely inspired by a disaster sociologist by the name of Daniel Aldrich, who has studied these disasters for decades and has proven what gets us all through a disaster is a sense of connection. And so what you need to do, in addition to the fabulous supply kit you've got and the wonderful plans that you've laid out, you actually do need to get to know your neighbors. And you do need to talk about this at work. And you do need to ask your kids' school if they've done a drill recently. More people get themselves through horrible disasters, especially no-notice ones, by counting on one another. It works. There's some fabulous literature out there that you can read about, and all of those books are listed on our website, but it's what we need to do. The last thing I'll save so that we can get on to questions, and again, this is amplified over with our community volunteers on the side of the room. Through researching disasters for a long time, we realized, especially in earthquake country, people naturally are very altruistic within the early hours and days of an event like an earthquake. And so we thought, what can we do to help make that what can we do to help make that connection happen? And so we worked with a lot of community members throughout the entire city to say, where close to where you live or go to work or wherever you spend your time, you tell us where a natural meeting place is so that if you needed to help one another out, you could. Anybody want to guess how many firefighters we have on duty tonight? 200? Very good. About 210. And all of them are absolutely spectacular. But they team up, and so there's only about 35 apparatus that they all ride on. That's the same number we're going to have on the day of the earthquake. What you can count on, though, is another 730,000 people who live here, who have taken CPR training, who have taken classes like this, who have organized themselves into groups willing to help one another out. This works. Community hubs are simply locations where we encourage people who need help and people who can help will get themselves together. I'm going to go ahead and abbreviate myself so we can get to questions, because I bet you guys have a lot of things you want to ask us about. So fellow presenters, come on back up again.
I was curious about the intervention of, I've been a little bit obsessed with gas, the gas shutoff. And particularly the opportunity to have that in homes feels like, and I'm curious, what other kinds of interventions like that would if you could sort of have a wish granted that you would be able to get people to do, would you want?
Learn about the rest of your utilities. Is this on? Okay. Learn about the rest of your utilities. So automatic gas shutoff valves, great idea. If you're doing this in your home, be aware of the fact a professional needs to be able to restore the gas after the shaking itself. But learn where you could turn off your water so it doesn't become contaminated with other damage that's been done in the system. You got a lot of water in your water tank. Some of you have a lot of water in your water tank, and you get to know your neighbors in case you don't. But think about what else you can do to kind of shield off your home, and then share. It's stone soup. And actually, a lot of people do this naturally during power outages. I do. I always take the dog for a walk out in the neighborhood and start talking with people about what it was they experienced. Last mile is an important point that you brought up also. Seattle is participating in an 8-county-wide planning effort right now, regional catastrophic planning, in order to identify, with a lot of good information from transportation managers, geologists, and other, where are the most likely places, once we can get supplies into the area, that we could put points of distribution, so that I can, within the course of the grant, within 2 years, be able to give you with a certain level of confidence exactly where am I going to drop off food, water, sheltering materials, et cetera.
Sir?
Minor question for Dr. Worth. You showed simulations of the M9 earthquake, and it happened in 10 seconds. Can you give me some idea what the time scale was for the arrival of the shaking and the duration?
Yeah, so the actual rupture does take some time. It's more like on the order of a minute or two, I would say. And then the duration of, or a few minutes actually. And then the duration of shaking, so we often like to compare this to Nisqually. So I think Nisqually was about 20 seconds or so of strong shaking. Someone on the stage can correct me if I'm wrong. And for the Seattle area. And then for a magnitude 9 earthquake, we would expect that it would be more like 100 seconds of strong shaking. So about 4 to 5 times longer for a magnitude 9 earthquake for the duration of shaking in the Seattle region. Yeah, so it's maybe a little bit longer than you thought based on the simulation.
Hi there. Thank you all for coming tonight. My question for John Hooper. You spend most of your time for residential and commercial structures. Is there any history or performance data on liquid storage structures like tanks, water, petroleum, that sort of thing?
Yeah. As part of that ASE 7 standard, there's a whole chapter just dealing with what we call non-building structures, including water tanks, petroleum tanks, all of those tanks, and they are, if they're in earthquake country, are designed for size performance equivalent to what we do for buildings, and sometimes higher because of the contents.
Yeah, how'd they do? The
well,
history? Or,
no, well, we had a real-life example down in Chile of 2010, and the newly designed water tanks and petroleum tanks all did actually very well with a magnitude 8.8 event. So they designed very similarly to what we do here in the United States, and that was a great test of Mother Nature again, that what we do as engineers seem to work well for big storage tanks.
Can you speak to the small mom and pop residential rainwater tanks?
That is exempt from our standard, so I really can't talk about that one. So I hope they work fine.
Hi, this question is also for John Hooper. It's kind of, I guess, more leaning towards the structural end, and the simulated model that you showed of the tower, the tall office tower in San Francisco, to what extent is glass curtain wall covered in sort of the structural design of buildings?
That's a great question. Will we be raining glass down on the
Yeah.
street? Or that, again, looking at our standard that we use to design buildings too, given the design earthquake, we designed the glass not to fall off. So that's a pretty big event. So we have a chapter just for that,
Okay.
which is good. And even given the maximum considered earthquake, the one that occurs about every 2,000 years, and all the new buildings we've been designing around town, the engineering community, even the cladding itself is going to stay on. It's designed to stay on. So we've really upped our game, if you will, in the last, probably 15 to 20 years, thinking about the hazard to the public around our buildings to try to mitigate that situation.
Okay. So I guess for downtown Seattle, where there's all of these tall glass skyscrapers that are being built, the assumption is that the majority of them
The
are
majority of
built
the new
to
ones.
the new code.
Oh, yeah, the new
to-
ones, yes, yeah. I can't talk about 40 years ago. That's a
Sure.
different animal,
Yeah.
yeah.
All right.
So we're going to alternate, so please.
Three questions, but all fairly quick ones. Most of us over here in Seattle had thought that we were protected from the effects of the tsunami by having all of that land between us and the ocean. Looking at the simulation, it looked like it roared right into Puget Sound, right into Lake Washington, wiped out everything in a houseboat on Lake Union. Just wanted to find out, is that a correct perception that even Lake Washington's going to get hit by the tsunami?
So let me preface this as first. So I mentioned that there's a wide range of possible ground shaking scenarios when there's an M9 earthquake. There's also a wide range of tsunami scenarios. But we do expect of course, the largest, the most damaging tsunami is going to be along the coast. We will have a tsunami that travels down the Strait of Juan de Fuca and into the Puget Sound region, but that will take some time, maybe an hour and a half to 2 hours after the earthquake. So there should be plenty of warning for Puget Sound area residents that are right on the water to get off the water. And we don't expect the tsunami to be nearly as high by the time it gets that far inland. So I've seen some simulations of a magnitude 9 earthquake that show maybe a meter or so tsunami in the Puget Sound region. But again, it takes about an hour and a half to 2 hours to get that far inland. I don't know if anyone else wants to comment on that.
Well, I was just going to add one comment. We just had a student finished up her PhD looking at that, and she found a couple of spots in Puget Sound where there is geological evidence supporting a tsunami running ashore that appears to be correlated with some of the past subduction zone earthquakes. And in those particular areas, the model predicts up to a couple of meters of run-up. So in isolated areas, it could be quite a bit more than a meter, yeah.
Okay, I was wrong. That was going to be my quickest question, so maybe I better just do one other because I don't want to steal everybody else's thunder. A lot of the preparation seems to be dependent upon, or the reaction seems to be dependent on cellular telephony. How confident are we that our cellular networks are going to be there functioning and having access to power after things happen?
Not.
Damn it. That was a quick answer, though.
So, for instance, we've done a citywide duty to report policy discussion, and the members of my staff know you shouldn't expect a call, you shouldn't expect a page, you shouldn't expect anything over the radio. If you felt it, that was your call to come into work.
So this is not directly related to earthquakes, but I'm curious about all of our volcanoes along the Cascades. Will they be affected and become activated by any of these larger earthquakes?
It's an obvious potential question to say, well, if there's so much shaking, could it not shake something loose in a volcano? And there are examples from the past, from the last century of history, of volcanic eruptions that seemed timed sort of suspiciously closely with very large earthquakes, including the biggest earthquake we know about, the 1960 Chile. But when people really try to look at those sort of systematically and look for statistics of it, it turns out that if there's any correlation, it's very, very weak. I think the most you could say is that there's the potential. You could sort of make the hypothesis that a volcano that is balanced right on the edge of erupting anyway could be triggered by the ground motion, by the strong shaking that comes through from the earthquake. Other than that, we don't see evidence on a global scale that's a significantly frequent or likely event. Good news for us, at least.
Sir?
Yes, exactly.
My question is directed at Barbara Graff, and I'm not certain what your proper title is, El Jefe or Madam OEM or?
Barb.
Barb. Barb, thank you. There was a mention of a 2016 Cascadia Rising report. I may be the only person that ever read it, and it was refreshingly honest and horrifying at the same time. And it mentioned the pulling of resources into a disaster area, and said it wouldn't work. You had to shift to a push system, whereas the local area is so on its lips that the government, the national level, has to come in without us asking them. Can you talk a little bit about that for
Yeah, I'd
me?
be happy to.
Thank you.
Cascadia Rising 1 was the June 2016 functional exercise that involved 4 states, British Columbia, all 4 levels of government, public and private sector, 20,000 people participating all at the same time. And it was meant to simulate what does happen in a catastrophic earthquake like Cascadia, where all of western Washington is absolutely decimated. But where along the I-5 corridor, you've got the majority of the Washington state population shouldn't be expecting a whole lot of help or resources because of what's happened out on the coast. Eastern Washington, Eastern Oregon, a little bit better off. We did a lot of really, really in-depth planning with the National Guard to say what size planes need to make it to Fairchild, what size aircraft then need to make it to Moses Lake, what size aircraft then make it in. We planned with the Navy, with the Coast Guard, with all kinds of different people. And the assumption has changed over the years. It used to be, you know, we have an earthquake, my mayor calls the governor and says, this was horrible, can you help? The governor thinks about it for a while, contacts the president. That doesn't happen anymore for many different reasons. You'll see some of the improvements that we made, and we need to be honest and candid that we don't always get it right in these exercises. The whole purpose of the exercise is to break the plan so the plan becomes stronger and better with good assumptions. So in Cascadia Rising 2, scheduled for 2022, we'll be taking that to the very next level.
Yes, sir?
Oh, hi. In a major earthquake, can you speak to the frequency and magnitude of aftershocks so that, assuming we get the shake alert system working well for the first shock, kind of segue off the other question too is, in a major earthquake, can we not expect the system to work very well for an aftershock?
Yeah, that's a great question. And aftershocks are potentially a really key application of something like Shake Alert because you have people in already damaged buildings, ones where you're maybe right balanced on that edge of life safety, and you have emergency responders that have to decide whether to be in those places. We know that for a very large earthquake, typically there is a relatively predictable kind of sequence of aftershocks, and we expect an aftershock of a magnitude, 1 to several of a magnitude, maybe 1 magnitude scale down from the main earthquake, but with a significant potential of an even larger earthquake as sort of an aftershock. Then we kind of redefine it as the main shock and a foreshock. But and then drop down 2 magnitude orders of magnitude. You expect to go up by a factor of 10 of those. Another order of magnitude, even more. So you expect hundreds of aftershocks, and Anchorage saw this last year. The Shake Alert system has the potential to be incredibly helpful for those aftershocks, but it also has challenges. One is when they were coming very, very frequently, the system is going to be challenged to distinguish individual events. So in those first minutes to hours after the earthquake, when it's sort of an exponential decay of aftershock. So when many, many events are happening, that's going to be a challenge to the system, and that's part of the technical work that still goes on and refining it, improving it, making sure it can really detect those events. We hope, though, that it will become a critical component of that. And one of the products that the U.S. Geological Survey produces now for every significant earthquake is an is an aftershock probability forecast, basically, going forward. And it even gets updated every day, or maybe more often than every day, so that people, and California saw this with the recent Eastern California Ridgecrest sequence of earthquakes, where they're getting regular information about the likelihood of an aftershock in the next 24 hours. And that set of earthquakes started with a 6.4, right? And then it was stated that there was the non-negligible potential for an even larger earthquake, although typically aftershocks are smaller. And in fact, we had the 7.1, 2 days later, 1 day later, I forget. Yeah. So that's actually a crucially important part of it that I didn't get a chance to talk about.
Perfect. Sir?
In the larger earthquakes you guys have studied around the world, plus what we might expect here in the subduction Cascadia 9-point earthquake, what happens with utilities in terms of natural gas and sewer and water conveyance and electrical and transportation infrastructure? What have you seen happening? What survives the most? What damages the most? And what can we expect around here, possibly?
We've unnominated all of ourselves as being the experts.
So anybody in the audience want to take this one? We're good with that.
What I can say is, for instance, I mentioned that our Seattle Public Utilities recently did do a seismic vulnerability analysis of its entire system, where it draws its water from, how it pipes it in, how it distributes it, et cetera. And I know that Puget Sound Energy and other utilities are doing the same sort of thing. But you should expect disruptions to absolutely everything. And there are standards, just like John talked about for buildings, there are standards for lifeline components, such as water delivery, telecommunications, fuel, and other things like that.
I might want to add that just to put a note of one type of optimism on it is that we've seen a number of these very large subduction earthquakes around the world. The ones that around magnitude 9 or high 8s are not very common, but there's been a bunch of them. And Aaron talked about directivity. An awful lot of them push their seismic energy sort of from below the shoreline out towards the sea. And that's good news. And in fact, we look at Japan in 2011, Chile in 2010, go back to Alaska in 64. You can look at a whole bunch of earthquakes. And many times these very largest earthquakes, because most of the shaking originates from offshore, are not as damaging as we might anticipate for their scale from the earthquake directly. That's not to say we're out of the woods at all. But damage in real earthquakes is very patchy. You showed buildings that would collapse next to other buildings. I told you I experienced that Santa Cruz earthquake in 1989, and I want to tell you that large parts of the city were absolutely fine, whereas a house could be off its foundation, and the one next door so fine that the china didn't fall off the shelves, And that's just the nature of earthquake damage. Chile, I think after the Maui earthquake, had a lot of things that went wrong, but an awful lot went right. And they really didn't have a very, very large loss of life or even of property for the scale of the earthquake, 8.8. Yeah.
So I just want to follow up quickly. I participated in a study the city of Mercer Island did maybe a decade ago. And their concern was that they were going to be out of water after a big earthquake. And their concern was very warranted, because if you go under the East Channel Bridge of I-90 and you look up, all of the utilities that feed Mercer Island are hooked to that bridge and come from the east across that bridge span. And I think at the time the bridge, and probably maybe still be, was designed to withstand about 30% G shaking. And so they were very concerned that they were going to be literally cut off of everything. And so they redesigned their water tanks, bolting them down and reinforcing them to keep them from jumping around. And they got a permit from the state and the federal government to draw water out of Lake Washington for firefighting. Yeah. So it is kind of the thing of get to know where you live and where your utilities are coming from, and make sure that, you make sure you know that they might be able to make it through the earthquake. Jim?
I'm James Bila. I'm president and founder of Oregon Earthquake Awareness in Portland. I've been working on Cascadia for 27 years, about as long as Aaron Wirth has been alive. Portland and Seattle have been in a century-long test of wills to see who can prove first that if you do nothing, nothing happens. When 1980, Steve Malone was looking at the helicarder at UW when Mount St. Helens erupted, and I put a quote from him in an article I wrote in 2014. And he said the lesson of Mount St. Helens is that in some cases, even the worst case scenario can be exceeded. And what I would like to propose to Barb is that how we got to now isn't working, that what we really need as a community, you can always hire people to do what it is you want to do. So I believe we should have scenario earthquakes to what we can expect in Seattle, both from Cascadia and from local faults like the Seattle fault, would be island fault, that people can use to build a community to withstand the maximum earthquake on the Seattle fault, which is about the size of the recent earthquake in Alaska. But until we have that, we don't know what we have. And maybe I'd like everyone in the panel to explain to the audience what a 2,500-year earthquake is. Because if we don't have to worry about that one, what about the 5,000-year earthquake? What about the 7,500-year earthquake? What about the 100,000-year earthquake, which we're about due for?
I'll just start by saying I appreciate the comment, and we do study earthquakes around the world. Christchurch, New Zealand is one of our sister cities, and many of our staff members have been down there, including our elected officials, and come home with the lessons and understanding of the trauma that a community like that goes through. Our electric utility, Seattle City Light, has tried to figure out how do we do more microgrids throughout the city, so we're not quite as we're able to segment but not break. And be a little bit more resilient in how we come back up again. But you're absolutely right. If we're just thinking, if we're staying at home and making this up in our head, we're never going to test ourselves with the rigor that we need to put really strong systems in place. What is a 2,500-year earthquake?
Brian's the man on that. Just to comment on, I won't get into details of how you sort of extrapolate to longer recurrence. It's a huge research topic, whether Cascadia produces, just the same one sort of beat by beat over and over again every 300 to 600 years, whether there are long pauses and then extra large earthquakes or not. Those are big questions, some of which we won't have answers to until we've waited a few thousand years to see. But you can kind of look at the maximum size of an earthquake that just the geometry of the fault zone is capable of producing. And it could be bigger than our current scenarios, but maybe only up to as much bigger as, say, the 1960 Chile earthquake was. So we kind of know things about what at least the globe has experienced during this time. And there are, of course, the Black Swan event, things that are very hard to plan for. The biggest earthquake the planet can have in 100,000 years is bigger than what we've seen, clearly. But there is sort of a maximum scale. We can't, despite Hollywood movies, we're not going to get to a 10.5. You're just not. Faults aren't that big. Yeah, exactly.
I'd like to add one comment on the building side of things. When I talked about 500-year events and 2,000-year events, when you look at that, and this is my USGS colleagues providing us the information, in that return period time frame, we look at all the different events that could generate that kind of shaking. So for us, that's about a 7.5 now in the Seattle fault. I thought it was 7.2 until tonight. It's a magnitude 9 on Cascadia, and it's about a magnitude 7 deep. So in our design process here in the Puget Sound region, even though we have a return period attached to it, it has scenario-based shaking that we think about. And the shaking I showed you for that building in San Francisco was a magnitude 8 shaking on the San Andreas fault coming right at the building. The directivity thing, Aaron, that you described. So we do think about it in those terms of real scenarios, because if you keep this generic return period, you got to think about real events and what they will generate, what shaking they will generate at the building site you're designing.
Perfect. Yes, ma'am.
Yes, hello. My question is for Engineer Duke Hooper. What parameters you take on consideration to add a damper system in your building design?
Okay. What you're asking is more sophisticated technology in helping to resist earthquake energy absorption. That technology, called dampers, has been around for quite some time. The Japanese use it quite regularly. We actually use it at Safeco Field The roof is supported that way, and so is a Seahawks Stadium roof. T-Mobile, thank you, whatever. I'm old school, okay, Barb? So anyways, we don't use that technology as much as we perhaps could, but as I had mentioned, as we look towards improving our performance measures and we look at this thing called functional recovery to help reduce damage, I think that technology will become more important because that's the way we'll need to go to help reduce the damage to buildings and get us back into buildings faster.
Yes, sir.
My question's a little bit more specific and perhaps not answerable. You've talked about scenarios and testing under different building conditions. I'm wondering about the floating bridges and the locks, and if any studies have been done about those structures, and if so, what that might mean for us.
The only one that I can specifically address is the new 520 bridge. And we were asked about that in terms of if there's a big Seattle fault earthquake that produces a seiche in Lake Washington, where basically a big water wave where the wave is water sloshy back and forth, what should they look for in terms of a rupture to design for, and how big a wave would that produce? And they ended up settling, and I really almost hesitate giving you a number because I'm surely going to be wrong, but I think they settled on like a 12 to 15 foot wave. And they built for that. And that may have been changed in the final design, but they did take that into consideration for the new bridge. The old bridges, I don't think they even took any of that into design, to be quite honest.
And the locks?
I don't.
So we have talked with the U.S. Army Corps of Engineers and toured the locks and what their emergency plans are. It isn't that they're built to survive, but they do have a contingency plan. They have the ability to intentionally flood them with other materials, which will screw things up for a very long time, but limit the amount of damage.
And remember, the locks were built over 100 years ago, right, guys? Earthquakes didn't exist for us 100 years ago.
Yes, sir.
Just following on that, I was struck by our building engineer explaining how we are getting so much new information that codes keep getting revised. So I'm wondering, structures like the Space Needle or, us old timers, the Seafirst building, or, a lot of these skyscrapers that were built 20, 30 years ago, what in a 9.0 earthquake might happen to some of these high rises?
Boy, is the camera off yet or what? Clearly, we're progressing our technology and our understanding of the earthquake hazard and the shaking that can occur. We have been designing for earthquakes for this whole time frame, and I have done some studies of some tall buildings in Seattle that are older vintage. Their reliability to perform well is not quite as high as a new building. Rest assured that's the case. But it's interesting, in some of the buildings that we looked at, because of wind design pressures, we designed for wind too, the wind does blow here, for tall buildings is a big deal. And you get additional strength of the building because of that. What you don't have as good, as I mentioned, is the detailing or the connection of the pieces together. So that's not quite as resilient. So again, I like to just describe it as it will do okay. It's not as good as today, but just because the reliability isn't the same, it can't be. And I can't put a quantification to that because we haven't done enough detailed studies, because each of those structures that were mentioned are very, very unique, obviously. And it would take a detailed analysis like I showed on my little video to really understand how those structures might behave.
I mean, the Space Needle's fairly simple. I mean, what about that 1962 structure in a 9.0, do you think?
I don't know. I really don't. I don't want to make something up.
Not to be. Yeah. So I want to take these last two questions, and then we're going to take a break, and you can get a beer and go to the bathroom.
I'm
We're
going
going
to
to
beer.
stick around, so if you want to ask other questions, feel free to grab
Can
us
I
and
just
ask.
make one more comment to follow up on that last question? So this. Did you study the Space Needle? No. But I was going to mention that in terms of new buildings, I feel like the city of Seattle and the cities of Bellevue have been very receptive to new research related to earthquakes. So in December 2018, both of those cities actually updated their guidelines for the design of tall buildings based on the M9 earthquake simulations and basin amplification that we were seeing in those simulations. So for new buildings, I think that actually we've been very good about updating the design recommendations.
And just let you know that we were doing basin before that too, just not to the rigor that we found out from the M9 research. Yeah.
And Jeff Berman, who's part of your M9 project at UW, has modeled the Space Needle, I think. And I'm not going to say anything about the results because I'm no engineer. But there's work that's certainly been done to look at exactly that question.
Oh, good.
Yeah.
I did not know that.
Sir?
Lots of tremendously wonderful, interesting, and thoughtful information. So thank you for that. But one comment that I heard that kind of has stuck with me was the importance of networks, community as part of the resilience profile. I think we hear a lot about having food, having water, and less about that. And I'm wondering if there's actually any research about how other places that have functional communities, is there something that we could do collectively? Is there some research to point at what works? Yeah, just to unpack that some more.
There's an enormous library in Boulder, Colorado at the Natural Hazards Research Center, directed by Chief Executive Officer Lori Peaks. And she's a good friend, she's a wonderful colleague, and we learn from many of her research scientists. Again, we're not trying to make up what we think we're going to experience. These are people who go around and study these things constantly. And something else you said, we are influenced by the international community as well. So like I've been a member of the International Association of Emergency Managers for years and years. And so we're constantly hearing what did and didn't work in Italy, in Japan, in Hong Kong, in Chile, in Australia, et cetera. So yeah, there's a big body of research. But I do recommend the Natural Hazards Research Center.
Last question, sir.
This one is for Professor Tobin. You have many precise GPS stations scattered throughout. And they are, the good news, you've found periodic seismic silent earthquakes. The bad news that you found periodic seismic. What is this data telling you? What's it screaming at you? What do you think you're going to get out of this?
Yeah, so people have heard about the slow earthquakes, or what we call episodic tremor and slip. And, maybe people don't know that. The same GPS that makes, your phone know where you are, if you fix it to the ground and measure it continuously, we can actually tell where that point on the ground is down to sort of a millimeter or so and see how it moves. So we're actually measuring plate motions. It's not just sort of geology anymore. But so what's happening is, right, the points on the ground in Western Washington typically are actually moving that few centimeters a year towards the east, and it's because the plates are stuck together. But every once in a while, the portion under sort of the eastern side of the Olympics and just west of the Sound here and up across Vancouver Island down into Oregon decides for a couple of weeks to turn around and move the other way for a little while. And it slips a number of centimeters and then stops again, and it's associated with this stuff that I hesitate to even call tremor because that makes everybody think of earthquakes. It's actually sort of background seismic noise at a very low level no one ever feels. But we measure, thousands of these tremor events during one of these periods of slow slip. It turns out they're on a different part of the fault zone, deeper down the fault, closer towards the direction of where I showed you where the stuff comes from for the volcanoes, than the part that we're most worried about being stuck and locked, for the most part, we think. And so what happens is, though, that is moving the upper plate just a little bit the wrong way or back towards, and a hypothesis has been floated and is being thought about that is adding a little bit of stress to the sort of the back end, you might say, kind of kicking the bottom end of the subduction fault in the place we don't want it to be kicked because that could trigger an earthquake. There is this clearly has been going on. It happens about every 14 months in our region, kind of like clockwork. And we got lots of news media interest this August when it happened, but then it kind of turned itself off earlier than usual.
Have they seen this anywhere else in the world?
Oh yeah, absolutely. So these kinds of events are happening in Japan. They're happening in a number of subduction zones around the world, and even on the San Andreas Fault and other non-subduction faults. I guess the bottom line, to cut to the chase, is that there's some evidence that sometimes big subduction earthquakes are preceded by some sort of slow slip event, but many slow slip events happen without an earthquake that follows them. So they're sort of like foreshocks. You never know something's a foreshock till a bigger thing happens after something you saw. We don't have them as a predictive tool yet, but we're certainly very interested in studying those events.
Perfect. Thank you guys very much. Like I said, we're going to be here for a while. Yeah, thank you.